Hi friends. Perhaps some of you have questioned yourselves whether there is a way to understand and grasp better those textbooks of histology and the diagrams and mostly the microphotographs. Well, I'm a physician, a pathologist, and I like to draw, so I'm going to present you an overview of histology, mostly based on diagrams and drawings. This is not by any means to replace the luxury of bibliography that is present now on histology. There are amazing books that deserve to be tasted and really enjoyed. So I'm just going to share with you guys some facts. Let me get my markers here so to get started. Let's start now. The center of many of all these sciences and other sciences is, of course you know that, the human being. Okay, well we have concentrated on our own self from many angles, from the anthropology, sociology, philosophy, physiology, etc., etc. But from the point of view of form, shape, we have actually three sciences that I can mention. One of them is embryology. Let's put the blue one up here. Embryology, which actually shows you how the human being is developing and develops inside the womb. We have, of course, anatomy. Let me go this way. Anatomy. And histology. At the beginning, they sound like different sciences, that they have nothing to do with themselves, but of course you guys know that anatomy looks at the human being with the naked eye, with the fingers, using just glasses. And histology needs the use of a microscope, even a light microscope, or a electron microscope, or a digital form of microscopy. But anyway, we need to magnify that universe of cells that we have here. Now, unlucky you guys, I would say that in this 21st century, we are actually going beyond the boundaries of electron microscopy. We're going actually into the realms of molecular biology. Why? Because we are actually made in molecules. We have a myriad, billions and trillions of molecules in our cells and in our bodies, and we are scratching the surface of this universe of our molecular world. Now, it's important to remember that also we are going to need, besides needing some concepts of embryology to understand how we are made, we need the physiology. Well, the study of human function is embedded with the study of human form or shape. We cannot never understand the digestive system, for example, if we don't understand how it works, or we have an idea of how it works. So we're going to introduce some concepts of physiology. Okay, let's just say a few words about anatomy, so you just kind of put it in perspective. You know that anatomy has been here for ages, from the Egyptians and from before. But actually, it's actually in the past 100 years, since the Renaissance and André Vesalius, that it started to grow as a science. To that point, at the end of the 1900s, at the beginning of the 20th century, anatomy was a voluminous encyclopedic science that has had the need to kind of shrink a little bit to be for the physicians of all the studies of more of biological sciences to use the concepts more in a simplified and direct fashion. Actually, something similar happened to histology. In the 1960s and 70s, the books on histology were 2 volumes or really big volumes. And now they are in the shape of atlases or books in which they mixed the microphotographs and the wording. It's actually much easier, but they still include a significant amount of information that needs to be put together. Not mentioning all the others, pretty much all the visual data. Regarding the histology, of course, we have to just put here that we have the light microscope, which has been forever, from the beginning, increasing in complexity and in efficiency, and also the electron microscope. The electron microscope and the light microscope are not totally different. Actually, they both use a source either of light or electrons that is manipulated by lenses, and they actually reach a point in which they incide into a surface of tissues, pretty much a section of tissues. And they are going to give us an image. If in the case of the light microscope, we get color, and the electron is just black and white because color is totally impossible. However, with the electron microscope, we may have something that is quite remarkable, which is the possibility of having volume, having, for example, cells or parts of the tissues that appear in 3-dimensional fashion. That's the way, because the scanning electron microscope incites electrons in an oblique fashion, and are recovered also in an oblique fashion by a computer system that reconstructs the image into a volumetric image, which is astonishing, I would say. Sometimes these images are stained, and they are remarkable, quite remarkable. Now, to begin the study of histology, you need a tissue, and it could be usually for histology we're going to use just a normal tissue, any normal tissue that you can get, but also for pathology, which goes similar. You need a sick tissue, right? An organ that has some kind of disease. Let's say, for example, if you have a muscle, a skeletal muscle that has fibers, parallel fibers like that, and has a couple of tendons on both ends, you want to study it, and you cannot put the entire muscle. Of course, you just get a little sample, about a couple of cubic centimeters, something like that, which is going to be prepared for study. Now we're going to start a process that is going to end up in this tissue forming part of another substance called paraffin, or a plastic embedding medium, that is going to pretty much form one substance with the tissue. But at the beginning, we have to start from scratch. We have to fix it. We have to start with fixation. And we need formalin. Well, obviously, why do we fix tissues? Of course, if they don't fix them, they will just rot and start foul smelling, and we won't be able to do anything with them. Now, in order to be able to embed the tissue in paraffin, we go to the next step and we remove the water from the tissues to all the extent that is possible. So we dehydrate and we remove the water. In order to remove the water, you have to replace it with another substance. So you replace it with alcohol. Alcohol, 80, 90, 100%, increasing concentrations until it replaces essentially the water. Now, once we reach this stage of dehydration, we find out that alcohol does not get along well with paraffin, and we need a subsequent step, and we can call it clearing. Clearing, which is usually xylene or other clearing agent that cannot transform the tissue, makes it look like more clear, I would say, more transparent. But still, xylene cannot mix with paraffin. So what we do is put the tissue in paraffin and then heat it up so that with heat, about 60 degrees, xylene will evaporate, and then the tissue will be able to be embedded into in paraffin. Now, the next step is sectioning. So the problem of sectioning reminds you that we cannot go down into little tiny cameras and discover the universe of our own bodies. Sorry, we need to just get a piece of tissue, get a section, and look at it in it, which is a bidimensional representation of a three-dimensional object, which is ourselves. In other words, all the sections are going to be flat, and you are going to cut in an oblique or transverse or longitudinal fashion, structures like vessels, nerves, cells, etc., etc. And you have to use your imagination to orient yourself. And organs are somewhat a little bit busy, and they have really a number of structures. We don't use a pocket knife for that, obviously. What we use is a microtome. A microtome which the name means that to cut in a small way. It's an instrument pretty much, if you will, like an old radio or an old typewriter or something like that. It's heavy, metallic, and has a wheel on one side. And with that you move the blade. The blade is located in the upper portion or lower, depending on the instrument. And the tissue and the paraffin is going to be here, and you're going to get sections that are very thin. How thin? About less than 10 microns, 5 microns, 3 microns, and depending on the mostly embedding medium. If you have a plastic, embedding medium, you are going to get thinner sections and luxury of details, which may be very useful for certain materials, right? What do you get with the microtome? When, in spite of so much, such a big instrument, we have only little specks of tissue that are coming out. And those, obviously, they don't float in the air. We try to put them in a water bath. In a water bath, and so that it is easier for the person who handles them to pick them up. By the way, the person who does all these processes and manipulates and pretty much deals with all these issues is the histotechnologist in the hospitals. The histotechnologist, histotech. The histotech is a professional, well prepared, and does a fantastic job of, giving the pathologists or the students the slides that are already prepared, ready to go in using different techniques. Well, once we prepare the slide and we elevate a piece of tissue, if we take it to the microscope, we don't see anything. We were so excited that we just don't see, more like a little blurred situation, nothing. We need to stain it, of course, you know that. So I'm just kidding you. So how do we stain tissues? We stain tissues two ways. We do it, one of them is just by immersion in different solutions. We just take the slides, of course, there are instrument machines that do it all automatically, that are are dipped into different solutions, one after the other, and there are many of them. The most common is the hematoxylin and eosin. I'll just put like that. The hematoxylin, which is blue, and the eosin, I put my red marker here, the eosin. In common terms, we use it the H&E, like everything is abbreviated, H&E. Hematoxylin and eosin. Of course, we have other stains that are prepared in a similar fashion, like Van Gieson, like Trachom, reticulin, mucin, many stains. It used to be many more before. But now, and you probably are familiar with, we have the possibility of staining specific molecules, specific parts of the cell that will give us the possibility of making diagnosis and visualizing things that we would never dream before. That is the immunoperoxidase. Pretty much the immunoperoxidase technique, which is based on the monoclonal antibodies. So monoclonal antibodies are prepared in a complex way, and there are actually different ways to explain it. The one I would just show you or explain you in a simple way. It's a little bit oversimplified. You get a cell and you analyze one area that you want to produce an antibody with. That's easier said than done, but you can do by different centrifugation and other methods, obtain one little area or substance. So to inject that to a rabbit or to another animal in the lab, let's just put it like that. Okay, what happens when we immunize an animal like a goat or a horse or any other animal? We will produce antibodies against these particles. However, what we are going to get is not a single antibody. The animal produces multiple antibodies. Why? Because this particle, although it's very minute, very tiny, has different areas, and there are antigenic determinants or epitopes that induce the formation of these antibodies. So what do? Now, we have to sacrifice the animal, poor little rabbit, and take his or her spleen and put it and get different clones of cells in different wells, let's say. These are wells, I would say, just oversimplifying, in which lymphocytes or antibody-producing cells are in each well. That's an oversimplification, but it tells you that different antibodies will be produced from it. Now, easier said than done. You discovered that one of them, let's say, for example, this one, is going to produce the monoclonal antibody that you want. So what you do immediately is you separate this cell, and then you hope and pray that this group of cells or this clone is going to produce a lot of monoclonal antibodies, which doesn't happen. these cells will probably last hours or maybe a couple of days, if more, I don't know, a small amount of time. So you need to fuse it to produce a hybrid cell with a malignant cell that is commercially available, a multiple myeloma cell. This is a multiple myeloma cell, malignant cell that is essentially immortal because it just keeps on multiplying itself. And we'll take the genetic material from these cells and start producing an amazing thing, which is a monoclonal antibody, which goes exactly the way that we want it. Not only it's unique, but it is in large amounts, so that we can manipulate and commercialize it, accordingly. Now, this actually was produced in the late 60s and early 70s, and a Nobel Prize was given to this group of British scientists, including an Argentinian scientist, Cesar Milstein. Now, what do we do with these antibodies? If these monoclonal antibodies are pretty much, if we allow them to fix to the cell, yeah, there will be a reaction, but you don't see it. You need to magnify. You need to make it evident. And what do you do with that? You add this series of immunoperoxidase components, so that whenever the antibody attaches to the antigen, it will light up. Voila! You're going to see the color, which is usually brown. It could be red, maybe other colors. I'm not familiar with that, but usually the two colors that I am. Now you see either in the nucleus or in the cytoplasm or in the membranes, the antibody will light up and give us a possibility of amazing possibilities. Now, there's also something else that I could share with you, guys, is the fact that these antibodies, from the beginning, since they pretty much from the later part of the 20th century, people started visualizing the possibility of using drugs attached to antibodies, so that the treatment of diseases with monoclonal antibodies and drugs started to grow and is amazing, growing incredibly. One little tiny caveat is that these antibodies are being produced by an animal, and if it's introduced into the organism, the possibility of immunological or anaphylactic reaction could be, it's to be expected. So what they do is they humanize segments of this molecule so that there is little or no reaction to the antibody, so that the immunological reaction is minimized. Now, how this process that I told you is magnificent, in a magnificent fashion, in the hands of the histotechnologist, it usually takes days, a couple of days, 3 days, 4 days, depending on the country and the hospital. Now, is there no way to make it fast? Because you would say, I have my breast biopsy today. I need to know immediately, as soon as possible. So yeah, ways have been devised to make this process faster. And actually, what we do is we introduce heat in the form of microwaves. Microwave system, I would say. Not that you're going to use a normal microwave and use alcohol or slightly input, maybe the whole thing will be explode or the whole hospital will be on fire. These solutions have been changed in such a way that they have exactly the same results, but they use a microwave machine, which the ones as I know are rather big, almost like a size of a couple of big refrigerators. But they produce, they give us the result of a processed tissue in about 2 hours. So, or less, depending on the equipment. So that is incredible, and it makes things much faster. There's only one other thing that I like to mention to you guys. Some people may remember that when the patient is in the operating room, a biopsy of tissue may be taken to pathology, and this tissue will be sectioned immediately, and the frozen section will be performed. Frozen section. Well, the frozen section means that the tissue will be cut frozen in an instrument that produces, it's almost like a small refrigerator that's very, very cold. This instrument is smaller than that one. It looks almost like a small refrigerator and has a sliding door, usually, and a microtome here. And obviously the tissue will be here. The blade will be on top. And the way we are able to do these sections is because there is a gel, a special gel that hardens with cold and that makes a single unit with the tissue, and you can get sections and they can stain with H&E or any other system that you want. So that is another way that we go. This instrument is called the cryostat. Finally, we will just mention one single detail that when you start looking on the set of slides that you got, or any slide, even in pathology, remember that low power is the key. It's not unusual to have students or even professionals who run away and try to look at the greatest possible power to try to see more. And actually, in histology, as in many things, less is more. It's like if you wanted to recognize, they tell you to make a certain study of a particular town or city, and you don't need a magnifying lens for that. You rather have a drone that will enable you to get perspective. It's amazing, but for a pathologist or persons that are with more experience, the low power is the one that's mostly used and probably the most useful of all of the other lenses. You only go down if you need to. Now, in the next weeks, I'm going to keep on going in a similar way, trying to give you mostly the essentials, the main concepts. Have a great day.